It is early October. Just after 5 in the morning. The yard is still dark at the edges, and the first light comes in gray and flat across the lawn. A white-throated sparrow lands on the feeder post, looks left, looks right, and begins to eat. A hermit thrush moves through the low shrubs at the back fence, unhurried. The air smells of wet leaves and cooling soil. These are birds you recognize. Birds you have seen every autumn at this time, in this yard. Nothing about this morning feels unusual. But the hermit thrush in your shrubs left its breeding grounds in the boreal forest of central Canada 3 days ago. It flew at night. Through total darkness. Over terrain it has never seen before. And it landed here, in this specific yard, in this specific town, because something inside its body told it this was the right place to stop. Science knows it happened. Science does not fully know how. This is not a metaphor. It is not poetry about instinct. There are peer-reviewed papers, published in Nature, in PLOS I, in the Journal of Experimental Biology, that describe the mechanisms involved. Researchers have isolated proteins inside the eyes of migratory birds that may allow them to perceive Earth's magnetic field as a visual experience. They have measured the quantum processes happening inside those proteins. They have confirmed the disruption caused by artificial radio waves too faint for any instrument you own to detect. The data exists. The papers exist. The mechanism is confirmed in outline. But the actual experience, what the bird perceives, how it computes the answer, how a brain smaller than your thumbnail integrates magnetic fields with star maps with smell with sound and produces a navigational decision, in real time, in the dark, that part remains unresolved. Welcome to this channel. We cover bird behaviors that science has documented but cannot yet fully explain. If that sentence interests you, subscribe now, because we publish one of these every week. And stay with this video to the end, because in the final section, we are going to cover a journey so extreme that the bird's body physically consumes itself to complete it. Not as a dramatic flourish. As a confirmed biological fact. And what happens in the last 12 hours of that journey is something researchers are still actively trying to explain. Most people who feed birds assume that migration is directional, that birds simply know which way is south, and they follow that direction until the weather warms. A built-in compass. Simple. Reliable. The scientific reality is more layered than that. Migratory birds do not use a single navigation system. They use at minimum 4, operating simultaneously. Magnetic field detection. Star map orientation, calibrated during the first weeks of life by watching the rotation of the night sky around Polaris. Olfactory mapping, a spatial memory of smell, built up over previous journeys and used to identify specific locations by the chemical signature of the air. And infrasound, low-frequency sound waves, below the range of human hearing, generated by ocean waves and mountain ridgelines, that birds may use as a landscape-scale acoustic map. Each system is documented. Each has experimental support. But how they are integrated, which system takes priority in which conditions, how conflicts between them are resolved, what the bird actually computes when the stars are clouded and the magnetic signal is ambiguous, no one has mapped that process. What makes this genuinely strange is this: birds raised in isolation, who have never migrated, who have seen no other bird migrate, orient correctly on their first flight. The map was not learned. It was present at birth. But in what form it exists inside the nervous system, that has not been located. The most precise work on magnetic navigation has focused on a protein called cryptochrome, found in the eyes of migratory birds. Researchers at the University of Oldenburg confirmed in 2022 that cryptochrome molecules in the European robin, Erithecus rubecula, undergo a quantum process, specifically, the formation of radical pairs, when struck by blue light. This quantum reaction is sensitive to magnetic fields. It changes depending on the angle of Earth's field relative to the bird's eye. The hypothesis is that this reaction produces a brightness gradient in the bird's visual field, something the bird sees as a pattern of light and shadow that shifts as it changes direction, effectively overlaying a compass on its visual perception of the world. The protein is real. The quantum reaction is real. The magnetic sensitivity is real. What makes this genuinely strange is this: European robins in the Oldenburg experiments were completely disoriented by radiofrequency electromagnetic noise at just 50 nanotesla, a field strength so weak it is 1,000th the strength of the ambient magnetic field, weaker than the signal from an unshielded power cable at 50 meters distance. The birds could not navigate. They lost all directional orientation. But when shielded from that noise, in a metal cage blocking artificial radio frequencies, their navigation was perfect. The cryptochrome system is so sensitive, so precisely tuned, that human-generated radio interference, the background noise of any modern city, is enough to break it. What that sensitivity implies about the precision of the underlying mechanism is something researchers are still working to understand. Now consider what that navigational system is actually required to do. The blackpole warbler, Sitophaga striata, weighs between 11 and 14 grams. It breeds in the spruce forests of northern Canada. Every autumn, it flies non-stop from the northeastern coast of North America across the open Atlantic Ocean to South America, a journey of approximately 2,700 miles, completed in 72 to 88 hours, without landing, without eating, without drinking. There is no land beneath it. No landmarks. No visual reference points beyond stars and horizon. For 3 days and nights, the bird navigates entirely by the systems described above: magnetic field, star orientation, possibly infrasound from distant coastlines, while its body burns through fat reserves and, toward the end, begins metabolizing its own muscle and organ tissue. Here is the scale moment. Before departure, a blackpole warbler may weigh as little as 11 grams. It doubles its body weight in pre-migration feeding. By the time it reaches South America, it may weigh less than it did before it began eating. The calories required to sustain 88 hours of continuous flight over open ocean are so extreme that the bird digests portions of its own digestive system to fuel the final hours of the crossing. What makes this genuinely strange is this: the navigation remains accurate during this process. As the bird's brain is being sustained by metabolized tissue, as the body is consuming itself, the cryptochrome system continues to function. The magnetic map remains readable. The bird lands where it intended to land. The mechanism that keeps navigation precise under those physiological conditions has not been explained. The most extreme documented migration belongs to the bar-tailed godwit, Limosa laponica, a shorebird that breeds in Alaska and overwinters in New Zealand and Australia. In 2022, a juvenile godwit, a bird making its very first migration, with no prior experience, having never seen the route, flew from Alaska to Tasmania in 11 days. Non-stop. 7,580 miles. No food. No water. No rest. It was tracked by satellite. The data is unambiguous. Researchers monitoring the flight noted that the bird's navigational accuracy remained consistent across the entire crossing, including the final 2 days, when it was flying over the open Southern Ocean with no land in any direction for over 1,000 miles. It arrived within 40 kilometers of its target destination. What makes this genuinely strange is this: it was the bird's first flight of this kind. Whatever navigational knowledge it was using, whatever internal representation of distance, direction, and destination it carried, was not acquired through experience. It was present on departure. How a juvenile brain encodes a target it has never visited, across an ocean it has never crossed, in a format precise enough to land within 40 kilometers after 11 days of continuous flight, is a question the satellite data cannot answer. It is early October. Just after 5 in the morning. The yard is still dark at the edges, and the first light comes in gray and flat across the lawn. The white-throated sparrow on the feeder post is reading a magnetic field with quantum processes happening inside proteins in its eyes. The hermit thrush in the back shrubs arrived here from central Canada by integrating star maps, magnetic gradients, olfactory signatures, and infrasound into a navigational decision that took place, continuously, for 3 nights of flight. The yard has not changed. The birds in it have not changed. But what they are doing, right now, at this moment, in the ordinary pre-dawn light of your ordinary backyard, is something that the best-equipped research facilities on Earth have confirmed, studied, and partially described, and still cannot fully explain. The instruments are real. The proteins are real. The quantum reactions are real. The journeys are documented by satellite, gram by gram, mile by mile. And the mechanism that makes all of it work, the actual process by which a 12-gram bird encodes a destination it has never seen, navigates to it across an ocean in the dark, and arrives, remains, at the level of complete understanding, unmapped. That is what is sitting in your yard this morning. If you have ever watched a bird in your yard in autumn and noticed it sitting very still, oriented in one direction, for longer than seemed normal, I would genuinely like to know what species it was and what time of day you saw it. I read every comment.